Hello, we have been discussing design methods for compliant mechanisms. We have discussed so far 5 different design methods, and today we are going to discuss a 5th one, and then in the next 2 lectures we will discuss a 6th one. These are the ones that one can say they are distinctly different from one another, and that is why we have chosen to discuss these. Today's method is a very elegant and very simple method. It has its own limitations, but it is something that we can teach even a high school student how to design compliant mechanisms. The concept is something that everybody learns during their undergraduate education in mechanical engineering when you learn kinematics, but that is very cleverly is adapted to design compliant mechanisms as we see today. It is called instant center based design method. So, it is a graphical method. So, something that we need to notice, it is a graphical method. One can actually do it on a piece of paper, maybe with a ruler or some measuring thing, but you do not really need anything analysis to design compliant mechanisms using this, and uses the concept of instant center of rotation. We did not write the rotation here, but actually instant center of rotation of a rigid body. That is again a kinematic concept. So, first let us discuss what instant center of rotation means. If I take a rigid body, so what we have shown here like a potato is a rigid body, something that we assume does not elastically deform. When you have such a body, let us say there are 2 points, let us call them A and B, does not matter, just labels. Let us say that point A has a velocity V A indicated by this arrow here, point B has a velocity which is indicated by this arrow. So, we have a rigid body in a plane, planar motion, we have 2 points which have velocities as shown here. If I take some other point on this rigid body, we can actually compute the velocity of that by knowing the velocity of 2 points in a rigid body in a plane, moving in a plane. It is a planar rigid body moving in a plane. Once we know 2 points and their velocities, we can get the velocities of any point on the rigid body. That is the nature of the rigid body. But how do you find that? There is one concept that every rigid body will have a point which may not be inside the point. When you say rigid body, it can be bigger, it can be this and that, it can be entire plane. So, if you think of it that way, there will be a point in the plane which will have 0 velocity. That means that at that instant it will not be moving. So, if I take this point, it may have some velocity, this may have another velocity, this may have another velocity, but there will be one point which will have 0 velocity. If you look at the rigid body motion from that point, it appears as if rigid body is rotating about that point at that instant. That is why we call it instant or instantaneous, it is shortened form of that, instantaneous center of rotation. At this point, rigid body appears to be rotating about that point. Okay. In order to compute such a point which has 0 velocity, what we do is we draw a perpendicular at point A to the direction of the velocity. Velocity V A is there. So, it appears to be moving in the direction instantaneously, that is what velocity means, right. Magnitude does not matter here, it is just that its direction matters, and you draw a line perpendicular to the direction, that is one line. Similarly, at point B, you draw another line again perpendicular to the direction of the velocity of that point. They both will meet at a point, because 2 lines definitely meet at a point unless they are parallel to each other in a plane. So, you have this point, this now is the instant or instantaneous center of rotation, that is the instantaneous center of rotation for this rigid body at that instant. What is the instant? Instant is points A and B have this velocity that are shown here in those directions. Now, this point will have 0 velocity, it does not move at this point, but rigid body appears to be rotating about that point instantly. Why do we say that? Because if this is the point that is like a pivot almost, okay, at that instant because that is not moving, its velocity is 0, it is like a pivot. The whole rigid body, if I were to connect it with some rigid thing, let us say this all connected rigid body, at this point appears to be rotating about that point. Since rotating about, it is rotating about that point, if I take this line, so the line that we have just drawn, right, if I take this line, right, since this is fixed at that instant, the velocity of this point has to be in that direction, and in fact we can find the angular velocity of the rigid body at that instant, because we are given velocity V A and we would know this R A, that is from this instant center to point A, then I can actually find the angular velocity, because R A times omega will give you V A. So, we can actually find the angular velocity. Once the angular velocity, any other point I want to take, I join that to the instant center, then it is going to be perpendicular to that, it is going to be that. So, again we will have, let us say I will call this generic point P, then I will have R P, omega times R P, which omega we already got. Again omega is magnitude of V A, direction we already used, now we are using magnitude, divided by R A, right, we got omega. Once you know omega, velocity of any other point P, we can write it as this omega times R P, that is distance from the instant center to that point. Okay. But our idea now is only to calculate the instant center, because at that point it appears to be rotating about that is our interest. We are not interested in omega or finding velocity of any other point. Okay. We just want to find this instant center of rotation, and that is a concept you need to understand. Okay. So, when you have a rigid body and you have 2 points whose velocities are known instantaneously, this is true only for instantaneous. After that rigid body moves some other way, instant center may move from that point to another point, and if you join all of those, that becomes a locus, and that has its own significance in kinematics. That is, if you take this rigid body, if you roll it along this, you actually get the same motion of rigid body as this one does. Okay. Anyway, all that is not of our interest. Our interest is only to understand what is instant center of rotation is. You have 2 points and you just need to draw perpendiculars to the directions of velocities at those 2 points, then you get a point of intersection, that is the instant center of rotation. That point at that instant will have 0 velocity. Okay. Now, let us look at a 4 bar linkage. Now, this is a concept that came from linkages or rigid body kinematics. We have a 4 bar linkage. So, we have input and output. We can see that when this moves at that instant, let us say it is moving or rotating like that, its velocity of this point is going to be that way. In fact, whether it is moving that way or this way, let us say, does not matter, it is just the direction of this point is going to be along that line, because it is fixed here, it has to be that way. Okay. Similarly, if I draw a perpendicular, again this is a perpendicular to this point, it has to be that way. If it moves like that, velocity will be like this. If it moves let us say the other way, then velocity will be this way, but direction is that. Similarly, here if this moves like this point will move like that. If it moves the other way, then the velocity will be like this, but direction will be the same. Okay. Now, what you see here is that in a 4 bar linkage, this is what we call a coupler body, because everything is rigid there. Again, as I said, when you say something is rigid between 2 points, you actually can imagine an infinite lamina or a planar sheet which is connected to those 2 points. So, even though I have shown only this much here, this one, this has really no significance, you can make it as large as you want. Okay. Now, if you see, we have the same concept, we have a rigid body where we know the directions of 2 points, directions of velocities of 2 points, that is this point and this point. When you have that, we can do the same thing, right, drawing perpendicular for at that point and then this point, then we get the instant center of rotation. So, this coupler body at this instant appears to be rotating about this point that we have just found. So, this will be our instant center of rotation. So, the whole rigid body, that is the coupler body, appears to be rotating about that point. Okay. This is the concept that we can apply to a 4 bar linkage, also even bigger linkages. Whenever you know the velocities of 2 points in a rigid body, you can find its instant center again at that instant. Okay. So, this is the concept that applies to 4 bar linkages. Also based on that, one can design 4 bar linkages graphically. So, here in the context of compliant mechanisms, what do we design for? What do you want to design for? If you recall, so far our interest has been function generation. That is, if I have one point and another point, I say my input is in that direction. If I apply input in that direction, I want, let us say, output in that direction. That is the kind of problems we have solved with rigid body modeling based design method, as well as structural optimization based design method, especially the topology optimization method. That is what we had done. With regard to other design methods, it was different, but everywhere we had this notion that input given in one direction, we have desired outputs, or rather target output. We choose the point, if this is the input point, output point, we want this. So, can we get this? Now, you can see how that instant center of rotation concept could apply, because we have 2 points. Here is the point 1, which is the input, we have point 2, and we know how they should move instantaneously, meaning when you start applying force in a compliant mechanism, we would know the directions of the velocities, because you are applying input in the direction, target output in one direction, because when you say a point has to move, you want to apply force in that direction and you want target output displacement, this will be the displacement in a particular direction. So, when you have these two, we can actually apply that instant center concept. In between what is there has to be rigid for this thing to work. Now, we do not have a rigid body, yet instantaneously the concept works. That is the basis for the instant center method. We have 2 points, input 1 we know which direction it has to move, and output point which direction it has to move, it is our target or objective, and we try to design a compliant mechanism for that. That is what we design for. So, let us look at that method. The main reference for this work, principal reference, is the work of Charles Kim and Sridhar Kota and Yang Mo Moon. This appeared in the Journal of Mechanical Design in 2008, 8 years ago. It is a very simple and elegant and easy design method. Okay. You can look up for more details in this reference. Now, let us look at what they have done. They defined something called a compliant dyad. Again, the concept of a dyad is also taken from kinematics literature. So, when you have one body, okay, you take another body, this is a dyad because it has 2 bodies. This is body 1 and this is body 2, that is a dyad. And this what is used in kinematic synthesis of rigid body linkages, because if I have one dyad and then let us say I take another dyad like this. Okay. Now, I have 2 dyads and I would design these dyads in a way that I have specified some rotation for this, let us call this theta, let us say we call this rotation psi. Then I would actually design so that the other one also has the rotation psi and this one has some rotation, let us call it phi. That is, we design these dyads first, we do not design a 4 bar linkage, we will see how 4 bar linkage comes momentarily. We design dyads in kinematic literature where we take 2 bodies, one of them is specified to have some theta rotation, theta 1, theta 2, theta 3 and so forth, and other one will have psi 1, psi 2, psi 3 from first position to second, first to third and first to fourth and so forth. We have these angles of rotation. So, when we do that, similar to the precision part synthesis we had discussed in the first design technique we discussed in this course, you will get lot of diode solutions. One will be theta and psi, other will be phi and psi. To both of them psi is common, okay, and if you join them at this point, okay, then that becomes more like a rigid body, because it undergoes the same angular rotation and one point is common to it. So, we can actually join this becomes one rigid body, that becomes our coupler body that we discussed in the previous slide. So, we get this rigid body connected with two rigid things here. If I put a pivot here and pivot here, I get a 4 bar linkage. So, the diode concept came from kinematics, where you can put together two diodes and make up a 4 bar linkage, provided you use the same rotation and have a common point for the second or floating body. Sometimes it is called a floating body also, that is how it is done. So, here when you look at this compliant diode, what these authors mean is that this one is compliant. One compliant body, or what we are calling segment in this course, one compliant segment, and this one is more or less rigid, because whenever you make a triangular frame, they are all joined here, this becomes rigid. Okay. So, they say that if you have a compliant segment and rigid segment, you can do something with it. Okay. So, this is one concept they propose, it is like a building block, diode block, and then they also go to the 4 bar linkage, but now it is compliant. So, this is compliant, this is compliant, but this one they want it to be rigid, that this segment. Okay. So, now if we were to fix it here and fix it here, these are all, these two are compliant ones, this is compliant, this is compliant, in between you have a rigid one. So, we know that whenever you have a cantilever beam like this, instantly no matter how you apply force here, okay, if it has any component in the transverse direction, that is in that direction, it will tend to move like that, because with Suraj body model we know that 5/6 of this length, it appears to be pivoted there. So, it is going to move like that. Similarly, this is going to move like this, right, which way, this way or that way does not matter, but this is the general direction. So, once you have this, if you make this rigid, you have something that you want, that is given 2 points input output, that is our design specification, and the directions that we want. Let us say I have one here, another one, this has to move like this has to move like that. If I get this compliant 4 bar block, then I would actually be getting a compliant mechanism. That is the simple concept here. So, I have again two things and they belong to a rigid body, but rigid body is connected to two compliant segments. So, what is the rigid body here? If I look at this particular one, where is this point, there is no joint there, no kinematic joint, this is the rigid body. Again, rigid body can be as large as you want, that rigid body is connected to two compliant segments. So, one is this one, other is that one, that is the concept here. So, I have a rigid body, it is connected to one compliant segment, another compliant segment. Okay. In between what we join is just a representation for the rigid body, which we can show as if it is rigid one by joining a thick line or a wide line. So, now when I apply force on it, let us say I apply a force on this one, this point will tend to, if I apply a force somewhere, so that not there actually, maybe more like I should say, let me join that, this is a segment. So, let us apply a force somewhere here like that, that is how it is going to move instantly. That is its kinematic constraint at that point will move like that, then this will move perpendicular to that. Okay. Let us say we do not know this, right. Somebody gives, okay, there is a point here, when this is the input, and they would say this point has to move like that, output. Let us say you do not know this, okay. Somebody gives you this, can you get this is the question, okay. That is this method. So, if you know this, you know how it is going to, if you apply force there, if this is all rigid, which we have shown with the thick line, this will move like that, because the constraint here is such that it will make it go like that. But given here, can you go there, that is what this design method tells you. Okay. So, the method here, okay, is that okay, there is one more point for which I have to erase all this. Okay, there is a little graph that came up. Okay. What this says is that we said it is rigid, but how rigid is the question, how rigid, because there is nothing like a rigid body. So, for that what has been done here, which is too small for you to read, this is log of the stiffness ratio. So, let us say I take Young's modulus of this compliant segments and rigid segments. This is the stiffness ratio of the what is supposed to be rigid one to what is supposed to be compliant, ER by EC, that is a log 1. So, the 0 is somewhere here, and then there is 1 here, and this is 2. This is a log scale, this is -1 here, and this is -2. You can see how the geometric amplification, the GA, this one is GA, that is output display. Let us say this is the input here, if I call this input and this is output. What is U out by U in? Displacement out the output divided by displacement the input, the GA. Again you cannot read these numbers, this is 0.465 and goes up to 0.5, meaning that there is a little change. So, as you can see, if I make this more and more bigger compared to the stiffness of the compliant segments, it kind of tapers off and automatically goes there. After a while 100 times bigger if you do, then that is good enough. You can make that the stiffness should be so much bigger, then geometric ratio will just whatever that this is already 0.495 approaches little more than 0.495. So, relatively rigid means that if you make it 100 times, that is good enough. If you make it 10 times, that is somewhere here, that is also good enough, because the difference in the geometric ratio from here to here is very little. So, 10 times is really easy, just make it if you have some in plane width for a what is supposed to be a compliant segments, you make it twice as wide. Okay, that is the depth of the beam. Let us say this is D, you make it 2D. When you think about second moment of area, that is BD cube by 12, if it is 2D already becomes 8D cube, whereas here it will be just D cube. So, we get 8 times. So, getting 10 times or 100 times is not that difficult, you do not have to really change material as it is intended here. So, relative rigid, when you say, you should be 10 or 20 or 50 or 100 times more rigid than the compliant segments, more stiffer than the compliant segments. Okay. Using these diode, compliant diode and compliant 4 bar, this paper puts forth a method where if you have something like this, if it is fixed there and fixed here and fixed here, okay. Since it is fixed here, this point will move in that direction if that is the input. Okay. In fact, for these things, if you put forces here or there, its motion is kinematically determined instantaneously, again not for large displacements. Okay. This moves like this, since it is fixed here, this point is fixed there, this point has to move like that perpendicular to that. When this moves like that, now if you look at this one over there, this will move like that. Okay. And how does this point move? Then you can see that if you consider this as a rigid body, which it is, okay, and so is this should also be rigid, relatively rigid as we just talked. Compared to the other segment, Here this is the compliant segment, compliant segment, compliant segment, this is rigid and this is also rigid. Okay. When it is rigid, we can see how this point moves, because we have, if that point is moving like that, we have this line, okay, and if this point is moving like that, we have this line. Now this one here will be our instant center of rotation, that is our instant center of rotation. So it appears to be rotating about that. What appears to be this rigid body. So I can join from here to here, and this point will move in that direction, because now rigid body, this is moving in this direction, this is moving in this direction, perpendicular to that, this is moves in this direction. We can even compute how much it moves. So by using this compliant 4 bar block and compliant diode block, you can put together and get more and more amplification. There is some amplitude that comes from here to here. In this case, it appears to be amplified literally, because between here and here also there will be instant center that you can find, which you can find by extending this perpendicular to that and extending this, okay, again perpendicular to that. This is the instant center for the first thing, that is compliant 4 bar instant center is this, right. So this is moving like that and that is moving like this. How much more? We have the distance from here to here, whereas this one is from here to there. So there is amplification from here to here, again there will be amplification. So let us look at the finite element analysis done here. You can see that this point has moved there, this point moved a little bit more, and based on the distance, you know, we had the instant center here compared to this and this, there is not that much difference. How much ever this is moving, it is also moving like that. Okay. So we can do this very easily. So now let us look at first the assumptions made. The coupler body is assumed to be rigid, you have to make it much stiffer than the compliant segments here, and it is true only for linear, that means that small displacements range, not for large. Instantaneously it applies, it works, that is why it is called instant center method, and it is a good way to generate initial guesses for optimization methods, or for that matter pseudo body model based methods also. So let us take a few examples now. If somebody gives us a problem where this is input and this is output, target output, we want it to move like that, apply a force in the input direction, again always this is what we want to get out of compliant mechanism. Then this method says that you draw a line perpendicular to it here, and you draw a line perpendicular to that, you get the instant center. So this is our instant center, and once you have it, that is instant center of rotation, and you can actually pick any point here. So this is fixed now, this is fixed now, whether you fix it here or here does not matter, instantaneously wherever you fix, this compliant segment will have velocity in the direction, and same thing here, you can fix anywhere, that does not really matter for instantaneous motion. Okay. So that is how you get this. Now let us suddenly ask the same problem, we have input in the same direction, output point is the same, but we just want the output now to move in opposite direction. How do you do that? This is a non-intuitive specification. So obviously when I draw this line like this and like that, this instant center will not work now, because when this point moves like that, this point will move like this if we just join them. So that does not work, you have to do something else. This is where the compliant 4 bar and diode and this connecting them like block by block would help. So what we do is we take an intermediate thing and choose 2 instant centers, one here and one there, so that we can put together 2 blocks to get what we want. If you do that, the first one, and also choose a point, you can choose a point here, here, anywhere, does not matter, you choose a point. First of all, there is a choice in choosing first that direction, okay, that direction we first chose, and then the point later. Once you choose the direction, instant centers get fixed, Okay. Then you can take a point anywhere, let us say we take a point over there, we connect that, we connect this, we connect this, we connect that. So, this becomes rigid, rigid, compliant, compliant and compliant. Again where you fix does not really matter, you can fix it here, 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 does not really matter. So, with the 3 compliant segments and 2 relatively rigid segments, you get the specification met here. Okay. Then that point, intermediate point will move because that will be perpendicular to that thing here, whether you look at it from the later building block or the earlier building block. So, this is what we just designed graphically and you can see how this moves. So, this point is moving that way, this moving that way just like this arrow shows, and this point is moving that way. So, you got a compliant mechanism in 2 minutes, right. Even though it is a non-intuitive specification, when you move here, how does it go? You can get that. So, you can watch this for a while and study this method to understand. Now, let us take another one where we can be quantitative in our specifications. So, we have here we want a geometric advantage of 4, that is, this is let us say input, this is input, little arrow, and this is output where it should be 4 times that. We want 4 times displacement, okay, 4x, not x4, 4x. So, how do you do that? Then we can use for example this lever, that is easy, where this will be 1 from here to here, and if this is 4 times that, I get this, right. So, even inversion of the motion is also evident with the lever, but they are not interesting because these are the weak spots. So, we are not interested in those. So, can we do this using this instance center method? Let us say we take a design domain that has 2 units this way, 3 units that way, it is all graphical. Then you can choose this 2 stage, the direction we had chosen last time. So, similarly in the example, so here we have chosen a direction and 2 instance centers and connect them, we get this. So, we have block 1, first one and block 2, 2 4 bar blocks we put together to get this, because this is now compared to this is 1 unit from here to here, this is 2 units. Instance center, if I take this one, this moves 1, this moves 2 here, when this moves 2 here, this moves 4, because from here to here this is the instance center now, this is 1 unit, from here to here it is 2 units, again it goes. So, we got geometric amplification of 4, geometric advantage of 4, okay. And this is the finite element simulation, like a validation of this. You can see how much this is moving, how much this is moving and how much this is moving, it moves 4 times, okay. So, very easily we can do, and what we said, this is compliant, 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 rigid and rigid, you can actually see in the simulation also. So, this one is compliant because that is deforming, deforming and deforming, these also deforming a little bit, we are seeing, but we are going large displacement here, okay. But this one is relatively rigid, this is actually intended to be rigid, but it is in that sense this will be deviating from the intended motion, okay. This is not really rigid, this is question mark, but that is okay, you got a mechanism that works. Now, here is an exercise that we will work out. So, this is let us say geometric amplification 16 we want, input is in that direction, output is here. Now, if I join perpendicular to this, perpendicular to that, that itself becomes instantaneous, clearly we cannot do it in one step. So, we have to do it in 2 steps. So, in order to do 2 steps, if I want 16, so let us say we choose a point, okay. So, from here and here, so I have chosen this to be 4 units, this is 3 units, so this will be 5 units. I choose this as the instant center, okay. This is 1 unit and a point that moves here will move 5 times. If this moves by let us say let us call it x here, let us call this displacement x, which is in that direction, this will be 5x because this is instant center. So, now if I extend this further, I get another instant center. Let us do that in a different color. So, I have another one here, that is our instant center, and this angle here is tan inverse 3 by 4. So, we can actually get this thing here to be 4 by 3, because from here to here, that is 1 unit. So, tan inverse here, this angle is the same as this one, that will be again 3 by 4, 1 divided by 4 by 3, 3 by 4, that is 4 by 3. So, we have, if this is 4 by 3, that is this is 4 by 3, this is 1, this will be 5 by 3, again Pythagoras theorem. So, 4 by 3 square plus 1 square, square root, that will be square root of 16 by 9 plus 1, that will be square root of 25 by 9, that is equal to 5 by 3, that is 5 by 3. And from here to here, that is the second stage amplification we get. If this point moves like this point is moving like that, we have to join from here to there, okay. And that amplification, in that case, this thing will be, these are 5 units, 1, 2, 3, 4, 5, and then 1/3 there, 5 1/3, or it is 16 by 3. In the first stage, we got an amplification of 5x. So, x became 5x, and over here now we will have this one, this is 5x. So, it will be 5x into, we will get this other amplification, this is 16 by 3 that we got, and this is 5 by 3 if I take this instant center. So, that amplification will be 16 by 3 divided by 5 by 3, that will be 16 by 5. So, we get 16 by 5. So, I get 16x. So, what our target was. This is a graphical method. Now, let us complete the linkage by using a different color. So, we can choose any point here and fix it, the direction is important, and join this point to that, okay. And this is again we have to choose some point here, fix it like that, and now this should be rigid, this should be rigid, and then we are joining this to that. So, that should be rigid as well, that is the coupler body here, and then we will fix this anywhere, does not matter where you fix it, that is our thing here. So, when I take this compliant mechanism, which is now drawn in green color, when I put some x here, this point will move by 16x as intended. So, this method is as easy as that, just on a graph sheet you can do. Now, if I change it, or you should try an exercise for you now, you put whatever now, you put 10, 12, 15, 13, whatever you like, try to see if you can get that. When it was given as 10, one of my summer interns last year did that, was able to design and also 3D print, because that is available for everybody. We can make compliant mechanisms. So, very quickly you can design and actually 3D print and make that. So, the main points of this are that instant center concept can be applied to compliant mechanisms, and we need to remember that it is only instantaneous behavior, but that is good enough, because when you go to large deformations also, it will direction will be pretty much in the same thing, and coupler should be relatively stiff. We discussed that 10 times, 20 times, 50 or 100 times is good enough, and the stiffer you are compared to the compliant segments, the more accurate your intended behavior is. It is a very quick way. You can get a concept, that is the idea here. You can get a concept, or what we call the topology of a compliant mechanism without using optimization. We are not saying it is the best one, it is one solution that works. And this could be a great tool for generating initial guesses for optimization approaches, where you can do size and shape optimization later on, and more importantly this is a nice educational tool. So, when you want to brainstorm and get something, this is a great teaching tool, and anybody can design compliant mechanism. Okay. Again the further reading, this paper describes the method in detail, and some example that we have included should help you or make you feel confident that at least one design method you can master without having to work very hard. You have to just use your intuition as to whether one stage is needed, two stages are needed. The example that we worked out used 2 compliant 4 bars, but you can also experiment with taking the compliant diode also. Compliant diode basically removes one grounded compliant segment, and that is the only difference. So, you can create compliant mechanisms very easily using this design technique. So, we took a rigid body and we said that when you have 2 points rigid body whose velocities you know, you can get the instant center. Now, in a 4 bar linkage, it is a rigid body 4 bar linkage. That means that the fixed frame, which is this, that is rigid, and then we have this as rigid, this as rigid, and this as rigid. Now, if I focus on this, which we can call the coupler body, that is rigid. Now, in a plane, a mechanism is moving. When you have 2 points and you say that body is rigid, you can actually imagine a rigid body, whatever size, it is in the entire infinite lamina, you can think of that as a rigid body. When you take that, the concept that we just discussed, that you have 2 points, we have point 1 and point 2, whose velocities we know, because this is a rigid crank. When you rotate it, its direction is going to be that way. When it moves like this, it will be like that. When it moves in the other direction, it will move like that, but that motion is fixed. Similarly, when this moves like this will move, the velocity will be in that direction, and when I move it in that direction, it will be that way, but direction is known. So, velocity is here, perpendicular to that, this itself. Similarly, perpendicular to that, this itself. So, these two if we join, now this point here will be our instant center of rotation for the coupler body. This is the instant center of rotation for the coupler body, because we took 2 points on the coupler body. That is how we can get, and this point, if it belongs to the coupler body, will have instantaneously 0 velocity, just like we had discussed. Now, let us see, when you have a 4 bar linkage where everything is rigid, we are able to see that 2 points, one point moves like this, other point moves like this. Let us call this input with respect to the rigid body, this is the output. If this is the target output for this applied input, we are able to get a 4 bar linkage. In the same concept, we will see how a compliant mechanism can be also designed, and that is the essence of the instant center based method.